Next is acceleration, velocity and displacement of SHM. We are knowing the differential equation of linear SHM, that should be d square x divided by dt square plus omega square x is equal to 0. We can write this as d square x divided by dt square is equal to minus of omega square x. We are shifting this plus omega square x in the right side, so it should be minus of omega square x. Then this d square x divided by dt square is equal to a, and that is the acceleration of particle performing SHM. So d square x divided by dt square is equal to acceleration a, that is the acceleration of particle performing SHM. So if we substitute this here in this, then we can write acceleration a is equal to minus of omega square x, and this is the expression for acceleration in terms of displacement x, So a is equal to minus of omega square x is the expression for acceleration in terms of displacement x. As we are having d square x divided by dt square is equal to minus of omega square x, we can write this d square x divided by dt square as d by dt into dx by dt is equal to minus of omega square x. But what is dx by dt? Dx by dt is what? It is rate of change of displacement with respect to time, and that is equal to velocity v. Now we can write here d by dt into v is equal to minus of omega square x. Then we can write dv by dt is equal to minus of omega square x. Now we can write this dv by dt as dv by dx into dx by dt is equal to minus of omega square x. Then we can write dv upon dx into dx by dt is equal to velocity v. It is the rate of change of displacement, that is dx by dt, and it is equal to velocity v. So dv divided by dx into, we are substituting this dx by dt is equal to velocity v is equal to minus of omega square x. Next step we can write, we will cross multiply this dx. Then we can write here v into dv is equal to minus of omega square x dx. By cross multiplying this dx, we can write this step v into dv is equal to minus of omega square x dx. Next step we will do, that is integrating both sides, then we can write integration of v into dv is equal to integration of minus of omega square x dx. Then we can write integration of v into dv is equal to, we are taking minus of omega square outside here into integration of x dx. Then we can write integration of v into dv is equal to v square by 2 is equal to minus of omega square integration of x into dx will be equal to x square by 2 plus c, and this c is the constant of integration. C is what? It is the constant of integration. The next step we will do here, that we have to find out this constant of integration C, and to find the constant of integration C here, we will take A be the maximum displacement, A be the maximum displacement of a particle from its mean position or equilibrium position, and this maximum displacement of a particle from its mean position is also called as amplitude, So A is the maximum displacement of the particle from its mean position or equilibrium position. Let's say this figure here. This figure shows the motion of a pendulum about its mean position. So see here, this is the mean position of the pendulum here. This pendulum constantly moves backward and forward. So when it moves in forward direction, this is the extreme position on the right side of the pendulum. This position is the extreme position on the right side of the pendulum, and when it moves backward here, this will be the extreme position of the pendulum on left side here. So what is maximum displacement here? On the right side we will take it as plus A, and on left side we will take it as minus A here. So this maximum displacement of this particle from its mean position or equilibrium position, this maximum displacement is called amplitude of that particle. So we can write here, at extreme position, the displacement of a particle x is equal to plus minus of A, but at this extreme position, the velocity of the particle is equal to 0. So at extreme position, the displacement of the particle is the maximum displacement. So we will take that maximum displacement, x is equal to plus minus A, and at the extreme position, the velocity of the particle is equal to 0. So if we put v is equal to 0 and x is equal to A in this equation number 1 here, then we can write velocity is equal to 0 square divided by 2 is equal to minus of omega square. We are putting x is equal to A here, so it should be A square divided by 2 plus C. Next we can write here 0 is equal to minus of omega square A square divided by 2 plus C. Then C is equal to omega square A square divided by 2. So this is the equation for C, that is constant of integration, and it is equal to omega square A square divided by 2. Now we are substituting this equation of C in equation 1. Then equation 1 will become v square divided by 2 is equal to minus of omega square x square divided by 2 plus of omega square A square divided by 2. Then we can write here v square divided by 2 is equal to minus of omega square x square plus omega square A square divided by 2. These two will get cancelled here. Then we can write v square is equal to, we are taking omega square common here, then we can write minus of x square plus A square. Then v square is equal to omega square, in bracket we can write this minus x square plus A square is equal to a square minus x square. Now we are taking square root on both sides, then we can write square root of v square is equal to square root of omega square in bracket a square minus x square. So square root of v square should be equal to v is equal to square root of omega square is equal to omega into square root of a square minus x square, and this velocity, it will be either plus or minus, that depends on the motion of a particle or the direction of motion of a particle from its mean position. So the velocity depends on the direction of motion of a particle from its mean position. So it may be plus or it may be minus. So this is the expression for velocity in terms of the displacement x. As we are having the expression for velocity in terms of displacement x, that is v is equal to omega into square root of a square minus x square. Now we will substitute v is equal to dx by dt in this equation or expression of velocity. Then we can write dx by dt is equal to omega into square root of a square minus x square. Then we can write here dx divided by square root of a square minus x square. We are cross multiplying this square root of a square minus x square. So dx divided by square root of a square minus x square is equal to omega into dt. We are cross multiplying this dt here. Now we are taking integration on both sides. So if we take integration on both sides, then we can write integration of dx divided by square root of a square minus x square is equal to integration of omega dt. So integration of dx divided by square root of a square minus x square, that should be equal to the sine inverse of x upon a is equal to, we can write the integration of this omega dt should be equal to omega into integration of dt is equal to t plus of phi, and this phi is the constant of integration. This phi is equal to the constant of integration. And to find this constant of integration phi, we have to know the value of displacement x at any instant of time t. So to find this constant of integration phi, we have to know the value of x at any instant of time t. So we can write this equation of sine inverse of x upon a is equal to omega t plus 5, as we are shifting sine inverse on right side, then we can write here x upon a is equal to sine of omega t plus phi, and then we can write here x is equal to a sine of omega t plus phi here, and this is the general expression to find displacement x. This is the equation to find the displacement x. So we are having acceleration a is equal to minus of omega square x. Then we are having velocity v is equal to plus minus of omega in bracket a square minus x square, and then displacement x is equal to a sine of omega t plus 5. So these are the expressions for acceleration, velocity and displacement of a particle performing linear SHM. Particle performing linear SHM. Next we will find out the expression for displacement for two particular cases. So the equation for displacement is x is equal to a sine of omega t plus phi. This equation we can write it as x upon a is equal to sine of omega t plus phi, and if we shift the sign on left side, then it should be sine inverse of x upon a is equal to omega t plus 5. Now we will take case 1 here. In case 1, we are considering the particle starts its simple harmonic motion from mean position. If the particle starts its simple harmonic motion from its mean position, then the displacement x is equal to 0 and time t is also equal to 0, and if we put these values of x is equal to 0 and t is equal to 0 in this equation of sine inverse of x upon a is equal to omega t plus phi, then we can write here sine inverse of 0 upon a is equal to omega into 0 plus phi. Then we can write here sine inverse of 0 is equal to omega into 0 will be 0, then we can write here is equal to phi here. Then we can write phi is equal to 0, or we can write phi is equal to pi here, because sine inverse of 0, it can be 0 or it can be pi. So we can write phi is equal to 0 or pi here, and if we substitute this value of phi is equal to 0 in the equation of displacement, that is x is equal to a sine of omega t plus phi, then we can write here x is equal to a sine of omega t here, and if we substitute the value of phi that is equal to pi in equation of x is equal to a sine omega t plus phi, then we can write x is equal to a sine of omega t plus pi here, and this sine of omega t plus phi is equal to sine of omega t here. So here we are substituting the value of phi is equal to 0 or pi in the equation of displacement, that is x is equal to a sine omega t plus phi. Then we can write here x is equal to a sine omega t plus 0, that should be equal to a sine omega t, and then we can write x is equal to a sine omega t plus pi. We are substituting value of phi is equal to pi here. Then sine of omega t plus pi is equal to sine of omega t. So we can write here a sine of omega t. And this displacement of a particle performing SHM from its mean position, it can be plus or minus That means it can be positive or negative, and this depends on this positive and negative of the displacement depends on the direction of motion of a particle performing SHM about its mean position. So we can write here this x is equal to, that is displacement is equal to plus or minus a sine omega t. So x is equal to plus or minus a sine omega t, and this is the expression for the displacement when the particle performs SHM starting from its mean position. Next we will take case 2 here. In case 2, the particle which is performing SHM starts from its extreme position. So case 2 is what? When the particle performs SHM, it starts from its extreme position. So when the particle performing SHM starts from extreme position, then the displacement x at extreme position will be the maximum displacement, and that should be equal to a. So it will be either plus of a or minus of a. Next, as the particle performing SHM starts from the extreme position, so at the start time t will be 0, and if we put this value of x is equal to a and t is equal to 0 in this equation of sine inverse of x upon a is equal to omega t plus phi, then we can write sine inverse of a divided by a is equal to omega into t is equal to 0 plus of phi. Then we can write here sine inverse of 1 is equal to phi. Then we can write phi is equal to sine inverse of 1, that should be equal to 90 degree, or in radian we can write it as pi by 2. So as we are taking x is equal to plus a here, then we will get a phi is equal to pi by 2. But if we take x is equal to minus a, then it will be sine inverse of minus 1, and sine inverse of minus 1 is equal to 270 degree, and it will be 3 pi by 2. Now we are substituting these values of phi in this equation of x is equal to a sine omega t plus phi. Then we can write x is equal to a sine of omega t plus of pi by 2 here, plus of pi by 2. Then we can write x is equal to a sine of omega t plus pi by 2 should be equal to cos of omega t. And if we substitute the value of phi as 3 pi by 2, then we can write here x is equal to a sine of omega t plus 3 pi by 2. Then we will write x is equal to a sine of omega t plus 3 pi by 2 is equal to cos of omega t. So this is the equation for displacement when the particle starts performing SHM from extreme position, but it may be plus or minus here, and it depends on the direction of motion of a particle. So we will write here x is equal to plus minus of a cos of omega t. Now we will see how to take the plus or minus, that means the positive or negative sign, in the expression for the displacement of a particle performing SHM. See this figure here. This figure shows that the pendulum performing SHM here, and we are considering the pendulum performing linear SHM here. So this is the equilibrium position of the pendulum here, and this is the rightmost extreme position, rightmost extreme position of pendulum, and this is the leftmost extreme position of pendulum here, as we are considering the linear SHM here. That means the pendulum performing linear simple harmonic motion, and this linear simple harmonic motion starts from this mean position, that means from this equilibrium position. So here the displacement x is equal to 0 here. Displacement x is equal to 0, and as it moves towards rightmost position, we are taking this rightmost position as a positive extreme position here. So here we will take the displacement as plus a here, plus a. So displacement x is equal to plus a. That means this is the maximum displacement of the particle from its mean position. So we will take it as amplitude. So x is equal to plus a, and this is the positive extreme position. And as the pendulum moves towards the left side from the mean position, and this leftmost position we will take it as a negative extreme position. So here at this negative extreme position we will take the displacement as minus of a. So this is the technique to take the positive and negative signs in the expression of the displacement of a particle performing SHM, and this is all about the acceleration, velocity and displacement of simple harmonic motion. Next is the expression of displacement, velocity and acceleration at time t. So as we know that the expression for displacement x for a particle performing SHM at time t is equal to a sine of omega t plus phi. So this is the general expression for the displacement of a particle performing SHM at time t. Next we will write here velocity v is equal to rate of change of displacement with respect to time. So we can write here d by dt of a into sine of omega t plus phi here. Then if we take the derivative of this, then we will write a into derivative of sine omega t plus phi with respect to t is equal to cos of omega t plus phi into derivative of omega t plus phi with respect to t, that should be equal to omega. So the expression for velocity is a into omega cos of omega t plus phi at time t. Next we can write here the acceleration a is equal to rate of change of velocity with respect to time. Then we can write d by dt of what is velocity. Velocity is what it is, a into omega cos of omega t plus phi here. And if we take the derivative of this a into omega cos of omega t plus phi with respect to t, then we can write here a into omega, we can take the derivative of cos of omega t plus phi with respect to t, it will be minus of sine omega t plus phi into derivative of omega t plus phi with respect to t, that should be equal to omega. Then we can write acceleration A is equal to minus of A into omega omega square sine of omega t plus phi. So these are the expression of displacement, velocity and acceleration at time t. Next is extreme values of displacement, velocity and acceleration. So we will find out first extreme values of displacement. So for displacement, the general expression for displacement of a particle performing SHM at time t, that is x is equal to a sine of omega t plus phi here. Now at mean position, this omega t plus phi is equal to 0 or pi. At mean position, omega t plus phi is equal to 0 or pi. So if we put x is equal to a sine of 0 or sine of pi, then we will get the value of x at mean position is equal to 0. So the displacement at mean position is equal to 0, and we will take it as the minimum displacement of a particle. So x minimum is equal to 0 here. At extreme position, the omega t plus phi is equal to pi by 2 or 3 pi by 2 in radian, and if we put this in the general expression, then we can write x is equal to a sine of pi by 2, then it will be x is equal to plus a here, because sine of pi by 2 is equal to plus 1. And if we put the omega t plus phi is equal to 3 pi by 2, then we can write x is equal to sine of 3 pi by 2. Then as sine of 3 pi by 2 is equal to minus 1, so here x is equal to minus a here. So at extreme position, the displacement of a particle is maximum. So we can write here this x max is equal to plus minus a here, because at extreme position the displacement is maximum. Then we will write here x max is equal to plus minus a. Next we will find out the extreme values of velocity. So for velocity v, the expression to find out the magnitude of velocity of a particle performing SHM, that should be equal to plus minus of omega into square root of a square minus x square. At mean position, the displacement x is equal to 0. So we can write here velocity v is equal to plus minus of omega into square root of a square. So we will write this as v is equal to plus minus of omega into a, and this will be the maximum velocity of a particle performing SHM at mean position. So when a particle performing SHM, then at mean position its velocity is maximum, and that is v max is equal to plus minus omega into a. Then at extreme position, x is equal to plus minus a. But in this expression of velocity, that is equal to plus minus omega in bracket a square minus in square root of a square minus x square, we are considered this displacement as positive here. So we will put x is equal to plus a here. Then we will write v is equal to plus minus omega in square root of a square minus x is equal to plus a, so it should be a square. So we can write here v is equal to 0 here. So at extreme position, the velocity of a particle performing SHM is equal to 0. So we will take it as minimum velocity of the particle performing SHM. So at mean position, the velocity of a particle performing SHM is maximum, but at extreme position, the velocity of a particle performing SHM is minimum. Next, we will find out the extreme values for acceleration. The extreme values for acceleration. As we know that the magnitude of the acceleration of a particle performing SHM, A is equal to minus of omega square x. So this is the magnitude of a acceleration of a particle performing SHM, that is equal to minus of omega square x. So A is equal to minus of omega square x here. So at mean position, displacement x is equal to 0 at mean position. So if we put that in this expression of acceleration, then we will write acceleration A is equal to minus of omega square into 0. So A is equal to 0, and this is the minimum acceleration of a particle performing SHM, and this minimum acceleration of a particle performing SHM is at mean position. Next we will take the extreme position. So at extreme position, we will write x is equal to plus minus a. So if we take x is equal to plus a, then we can write a is equal to minus of omega square into a here, and if we take x is equal to minus a, then we can write a is equal to minus of omega square into minus of a. Then we will write it as minus into minus, it will be plus of omega square a. So we can write here a is equal to minus plus omega square a, and at extreme position the acceleration will be maximum. So a max is equal to minus plus omega square a. So these are the extreme values of acceleration, and this is all about the extreme values of displacement, velocity and acceleration. Next is the amplitude, period and frequency of SHM. So first of all we will see the amplitude of SHM. See here, in this figure it shows the particle performing SHM along a straight line, and it will performing a SHM along a straight line from this M to N. So this is the straight path of the particle along which the particle performing simple harmonic motion. So we are considering here this is particle P here, and this particle P performing SHM along this straight path. So as this O is the mean position here, this is the center of this straight path Mn. So we will take this O is the mean position of the particle, and particle from this mean position moves from this O to P here. then we can write the expression for the displacement of a particle performing SHM. X is equal to a sine of omega t plus phi. The particle P which is performing SHM will have a maximum displacement when sine of omega t plus phi is equal to plus or minus 1. So the particle P which is performing simple harmonic motion will have its maximum displacement when sine of omega t plus phi is equal to plus minus 1. So when sine of omega t plus phi is equal to plus 1, then the displacement x is equal to plus a here, and when the sine of omega t plus phi is equal to minus 1, then the displacement x is equal to minus a. So x is equal to plus minus a is the displacement, or it's the maximum displacement of the particle performing SHM about its mean position, and this distance a is called as amplitude of SHM. This distance a is called as amplitude of SHM. So see here, when the particle starts its motion or moves along a straight path from this mean position O here, then when it moves to this point M, then its displacement x is equal to plus a, and when the particle moves from point O to this N, then its displacement is x is equal to minus a. So this distance a of a particle from the mean position is its maximum displacement, and this maximum displacement is called amplitude. So the maximum displacement of a particle performing SHM from its mean position or equilibrium position is called amplitude of SHM. Next we will see the period of SHM. So what is period of SHM? The time taken by a particle performing SHM to complete one oscillation, is called period of SHM. So the time taken by a particle performing SHM to complete one oscillation is called period of SHM. Now see this figure here. The particle performing SHM moves from this mean position O to this P in time t, and the displacement of particle from O to P is x. So we can write here the particle performing SHM having displacement at time t, that is x is equal to a sine of omega t plus phi, and we will take it as equation number 1 here. Then after a time t is equal to t plus 2 pi divided by omega, then displacement of the particle performing SHM will be x is equal to a sine of omega into, we are substituting this t is equal to t plus 2 pi by omega in this equation number 1. So we can write here t plus 2 pi divided by omega plus phi here, Then we will write x is equal to a sine of omega t plus of 2 pi omega divided by omega plus pi. We are multiplying this bracket t plus 2 pi by omega, then we will write omega t plus 2 pi omega divided by omega plus pi. This omega and omega will get cancelled here. Then we will write here x is equal to a sine omega t plus phi plus of 2 pi here, and by using the trigonometry here we can write x is equal to a sine of omega t plus phi plus 2 pi is equal to sine of omega t plus phi, and we will take this as equation number 2. From equation 1 and 2, we can write that the particle is at same position. The particle is at same position after a time 2 pi by omega. So from equation 1 and 2 we can write that here the particle which is performing SHM is at same position after a time 2 pi by omega. That means the particle which is performing SHM completes one oscillation, in time 2 pi by omega. So the time taken by a particle to complete one oscillation, this time is called as period of SHM. So we can write here period of SHM is denoted by capital T is equal to 2 pi divided by omega. So this is the period of simple harmonic motion. So when the particle performing SHM completes one oscillation, so the time taken by a particle to complete that one oscillation is called period of SHM, and here this period of SHM is equal to 2 pi by omega, because the particle completes its one oscillation after a time 2 pi by omega. So we can write period of SHM capital T is equal to 2 pi by omega. Next step we can write here, as we know that omega square is equal to k by m, then we will write omega is equal to square root of k by m here, and if we substitute this in this formula of period, then we can write t is equal to 2 pi divided by square root of k divided by m. Then we will write the period t is equal to 2 pi into square root of m divided by k. So this is the formula for period in terms of mass of a particle and force constant, that is T is equal to 2 pi into square root of m upon k. Next we will see the frequency of SHM. So what is frequency of SHM? The number of oscillations performed by a particle performing SHM per unit time is called the frequency of SHM. The number of oscillations performed by a particle performing SHM per unit time is called frequency of SHM. So here the particle performs one oscillation. In time capital T, that is period of SHM. Hence, in unit time, the particle performs 1 divided by T oscillations. In unit time, the particle performs 1 divided by T oscillations, and hence the frequency of SHM is given by 1 divided by T, that is n is equal to 1 divided by T. So as n is equal to 1 divided by T, this is the formula of frequency. So we can write 1 divided by what is period? Period is equal to 2 pi divided by omega. Then we will write here n is equal to omega divided by 2 pi. Then we can write n is equal to, what is omega? Omega is what? It is square root of k divided by m divided by 2 pi is equal to, we can write 1 divided by 2 pi into square root of k divided by m. So this is all about the amplitude, period and frequency of SHM.